Good evening, everybody, and warm welcome to this third edition of Professor V.V.S. Sharma Memorial Lecture. We were very fortunate to have very eminent speakers. Like first lecture was by Dr. Thomas Kailath, second was by Dr. K.S. Trivedi, and now we have Professor George Verghese. I'm really very grateful to all of you to be here. To start with, I will request Professor Rajesh Sundareshan, Dean, Division of EECS, to welcome the dignitaries and preside over the function. Thank you.
On behalf of the members of the Division of Electrical, Electronics and Computer Sciences of IISc, it's my privilege to welcome all of you to this memorial lecture, Professor V.V.S. Sharma Memorial Lecture, which will be delivered by Professor George Verghese. A warm welcome to the family members of Professor V.V.S. Sharma as well, and also a warm welcome to Professor George Verghese. May I request the grandson of Professor V.V.S. Sharma, Karthikeyan Sharma, to hand over a bouquet to Professor V.V.S. To Professor George Verghese. Yeah. Yeah.
Thank you.
I've heard that Professor V.V.S. Sharma was an outstanding mentor and teacher, and many of his students are at various places inspiring other generations, next generation of students. I'm actually eager to hear more about Professor V.V.S. Sharma from Professor Chiranjeev Bhattacharya. In Professor George Verghese, I think the committee, the organizing committee has found a very eminent person to give the talk, someone who understands the kind of work that Professor V.V.S. Sharma, and he's going to elaborate on that. So I'm looking forward very much to the talk. I also thank the organizing committee. Many of the organizing committee members are students of Professor V.V.S. Sharma, for enabling this event and for inspiring us to think about the kind of topics that Professor V.V.S. Sharma thought about, and also for inviting me to welcome all of you here. It's a privilege. So enjoy the talk.
Thank you very much. Now I request Professor Chiranjeev Bhattacharya, Chair, Department of CSA, to introduce Professor V.V.S. Sharma. Thank you.
Good afternoon to all of you. I have, in one sense, a very difficult job and also an easy job. So those of students of Professor V.V.S. Sharma doesn't need an introduction. His colleagues doesn't need an introduction. But maybe for the younger, next generation, maybe this introduction is necessary. But it's also, I'm a little bit emotional. Today I'm the chair of the department, but the first course I taught was taught with Professor V.V.S. Sharma. And it's very difficult to articulate, but I think I picked up several such things on how to teach some small facets. I do not have the words to articulate that. So let me get in the boring detail. I will read out his CV. And yeah. So Professor Sharma unfortunately passed away in 13th of January 2018 at his home in Bangalore. And his memory, I really thank the students, of his students who have conceived of this memorial lecture. And it's an honor to be here to hear eminent speakers talk about latest science. He's survived by his wife, Mrs. Shubhalakshmi, and his three daughters, Vijaya, Janaki, and Aruna. I think Janaki is here. Welcome. Professor Sharma was born in May 7, 1944 in Vijayawada. At the age of 17, he graduated with the University Gold Medal in MPC. Now, many of us, younger generation, MPC means multi-party computation. So this is mathematics, physics, and chemistry. Now, imagine 17-year-old University Gold Medal. So you can see his scholarly things. And after that, he came to ISc, finished his BE, ME, and PhD. And he then joined the ECE department as a faculty member in 1967. And of course, CSA stole him, and I do not know when, but since then, from his inception days, he has been a faculty member in the department, and continued till 2006. So and after that, I'm sure during his tenure, he went to various places in the United States, in industry, TRDDC, etc. He's been honored with several fellowships of Indian academies. But having said all of that, the primary reason, see, I was a student of this institute. I did my master's and PhD here. So one of the things that attracted me, these are 1993, 94, I saw a very vibrant thing, like a new program which nobody has any clue, is called machine learning, AI. You know, it's a very exotic field then. But it attracted me, and now today AI is everywhere. And then later on I learned that the vibrancy of that environment, Professor V.V.S. Sarma had an interesting role to play. If I'm not wrong, the first course in CSA department on AI was taught by him in 1970s. And of course, there are other colleagues there. I do not know the full history. Senior professors can correct me on that. So now from there, and I can proudly say of my seniors and of my colleagues, we have a very strong AI group. And without him, it wouldn't have been possible. And it's befitting that we have somebody like Professor Verghese coming here and speaking about latest science. Thank you all. I'm welcome to talk.
Thank you, Professor Chiranjeev Bhattacharya. Now I request Professor Vijay Chandru to introduce Professor George Verghese. Thank you.
Good day to all gathered here, and particularly to the attending members of the family of late Professor V.V.S. Sarma. I'm Vijay Chandru, a former colleague of Professor Sarma in the CSA department, and have very good memories of a 15-year association with Professor Sarma, including very useful conversations on the foundations of AI and logic-based reasoning systems. And his knowledge of Sapta Nyaya system of Jain logic was exceptional, and it helped me to understand the power of reasoning in such frameworks. We had offices across from each other, so a lot of corridor talk, right? It was always a pleasure. And thank you to the organizers for giving me this privilege of introducing our distinguished Professor V.V.S. Sarma Memorial Speaker for 2023, Professor George Verghese, the Henry Ellis Warren Professor of Electrical and Biomedical Engineering at MIT in Cambridge, Massachusetts. Professor Verghese joined the faculty at MIT in 1979 when I was a PhD student there, and became a mentor and friend soon after. His association with CSA department at IISc and IISc in general had begun in his PhD days, right? Student days when he spent time with his advisor, Professor Kailat, spending a sabbatical here, and over the years, George has continued with multiple visits and sabbaticals on campus, so we actually know him quite well here on campus as well. His research excellence and is well known, and we'll also see some of it during his talk. But I think it's important to note that MIT has a culture of putting its best researchers to teach foundational courses to undergraduates, right? And that's an extraordinary tradition of MIT, and it really distinguishes it from other universities. And Professor Verghese not only met the exacting criteria to be in this select group, but also has won awards for outstanding teaching and mentoring of undergraduate students. So in that sense, I think there's a nice similarity between what Professor V.V.S. Sarma stood for and what George has accomplished. Today, he will speak to us about his pivot from core areas of power systems and electronics into computational physiology for clinical inference. As his abstract mentions, abstract for this talk mentions, there is a similarity between the progression of the careers of Professor V.V.S. Sarma and his own, that they began with a grounding in electrical engineering and the classical sort of fields within electrical engineering, and then reached into application domains, leveraging that grounding. Right? I will also add that there is a similarity in their personalities, and both have been stellar examples of human beings with extraordinary grace. And with that, I'd like to pass it on to Professor Verghese to give his lecture. Thank you.
That's more generous than I deserve, but what do you expect from a friend? Yes. Thank you. Thank you, all of you. It's an honor to be here today speaking to you with the family of Professor V.V. Sharma present. Actually, the date might have just passed you by, but actually, let's see here, if I can get this to. It's actually exactly the 5-year anniversary of his passing today. It's a welcome coincidence, and I'm very grateful to be given this chance to talk about my work, and not directly connecting it to what he's worked on, but you'll see some overlaps and some similarity of approach, perhaps. So I found it very helpful as I was trying to put this talk together to go through something that he's written about his career. And this is something he actually wrote in 2017. The last version that I saw was September 2017, a few months before his passing. By the time it appeared in print, it was 2020. This is a series of essays by members of the Indian National Academy of Engineering, reflections on their careers, very different themes, and this is available online as a PDF, so I encourage those who haven't seen this to look at it, volumes 1 and 2. He's in volume 2. And so there's a little biography which highlights some of the areas that you heard about here, his work in fault-tolerant computing and optimal multiprocessor architectures, and aspects of AI applied to systems in various domains. So this is the actual title of his reflection, Engineering the Human Mind and the External World. So engineering the human mind is a nod to his interest in AI, but also to Indian philosophy and logic. And the question he asks is an interesting one. Is the mind of an engineer different from the mind of any other human being? And I'll leave you folks to come up with your own answers to that. And then what does a decade of training spanning BE, ME, and PhD do to the way a person thinks and acts? And he says, this article is my journey down the memory lane in the world of engineering education. And I found it interesting, that he would highlight engineering education as really the theme that runs through his work. He didn't say about research, he didn't say academics, he says engineering education. So you can see that his heart was the heart of a teacher first. And this was done, as I said, in September 2017. You've heard about his career, the milestones there, and I thought I would just put this up so that you can see it in one place, and his progression at IIC, starting with his BE. So the BE was, as I gather from what he says, in electrical technology in the EE section of the power engineering department at IISc. And then he went on to a career of research in AI, systems engineering, software engineering and reliability, and various particular applications, and was well recognized for that. This I found particularly fascinating, that his subjects in the BE, and he doesn't speak of these subjects with particular enthusiasm, but he lists them, included things like hydraulics, building construction, surveying, illumination, wood pole and tower design, I had to guess what that is, but your guess is as good as mine. No, you know what it is, but they had a course on that. And I'm just wondering, of the subjects that we're proud of today, in 60 years, which of them are they going to be mocking? Saying, you know, you'd spend university time on this? This is a full 60 years ago. Then he went on to an ME in power systems, and it's interesting that he says that's the stage, that's the stage at which...
copy.
Yeah, is that Zoom? I think someone on Zoom needs to mute. Please stay muted. Please stay muted on Zoom.
Oh, yeah. Oh, thank you.
Otherwise, we're going to have to kill the Zoom session.
Thank you. Thank you.
Professor Dikshitulu, I think you're unmuted. Could you mute, please?
No, I am. I'm able to speak.
No, okay. Actually, I might be able to. Oh, I managed to mute you. Okay. Thank you. I didn't know I had that power. Well, I think you just unmuted yourself. Okay. Okay, you don't have to do anything now but listen.
Yeah.
You're fine. Thank you. Okay, let's keep going. Yeah, so he says that it's at the start of his ME that he made the transition from thinking about components to thinking about systems. So the power system as an interconnection of components. Till then it was, you know, machines, transformers, wood poles, and tower design, and so on. So this was kind of a transition. And then when he came to do his PhD, this was a further leap into the systems kind of area and more general than the particular application of power systems. And this was done with Professor Dikshitulu. So I'm very glad that you're tuned in, Professor. So this was 1971 that he completed his PhD. And he was already, by the way, telling all these stories, I'm going to eat into time I have for other things, but I'll cut other stuff later. He was already co-authoring papers with other students there while he was working on his PhD. So he has several publications with Professor Sajendra Singh, who was a master's student at that time and then went on to a PhD, I think, at Johns Hopkins. He's now a professor at University of Nevada in Las Vegas. And then after his PhD, he, of course, had his own students. I've contacted one of them too, his first PhD student, Mansoor Alam, who is now head of department at Northern Illinois University. And they both, you know, remember him very fondly and how gentle he was. They both talked about his gentleness as an advisor and a collaborator. Okay. So I first met him, as was mentioned, when I came and tagging along with Professor Kailath when he did a sabbatical here. I was then a doctoral student. That's when I met Professor Vijayanatham too, who was a lifelong friend and colleague of his and collaborator. This was a time when I didn't know what my PhD was going to be about. So it was I was kind of floating, picking up things here and there and wondering where I would go with this. I continued from there to, with Professor Kailath, to the continuation of his sabbatical in Belgium. Some of the learning I did there turned out to be very important for what I did for a thesis. And then many years later, I came back for a sabbatical here at IISc and interacted with him then again. And there have been other meetings as well on other visits. Okay, so my own route is I finished a 5-year BTech at IIT in Chennai, IIT Madras, and then went for a master's at what's now called Stony Brook University, and then the PhD at Stanford with a thesis in the same sort of area that Professor VVS worked in. dynamics and control, some signal processing, and this was under Professor Kailath. And that was done in December 78. All of these degrees were in EE. So what I actually did my thesis on was something quite simple. It was linear time invariant models of this type. Those of you who've done control course recognize it with the E not there. It's just a standard linear time invariant state space model. But if you put a matrix E there, square but singular, then it turns out that interesting things can happen. If you allow arbitrary initial conditions in such a system with E singular, then you can get impulsive responses to those initial conditions, which you would never see in a familiar linear time invariant model of this type, with the E being the identity matrix. There you'd only see decaying exponentials or growing exponentials if it's unstable. Here you'll see actual impulses as the system adjusts from initial conditions previously that are inconsistent with the algebraic constraints embedded in the E over there. And as that adjustment takes place, you get impulsive motion. So it was actually a very simple thing. And the origin of that thesis was my sitting in a seminar like this, and Professor Rosenbrock, who was a luminary in the field, who'd started looking at these sorts of equations, was talking about what he did. And I realized that he was assuming initial conditions consistent with this equation, not arbitrary initial conditions. And as soon as you lift that, there's a more interesting and richer story. And 6 months later, my thesis was done, really. But what went into it was the learning I'd done on that sabbatical visit, partly starting here, but continuing in Belgium. So this is partly by way of encouragement to students here who are sort of floundering and wondering where their thesis is going. And it's just to say to forge on, to keep learning, and at some point this will all come together. And that seems to be how this works. Now the thesis and the paper that I finally completed on it a couple of years after starting my work are actually quite well cited. It turned out that this was interesting in many different domains. So I joined MIT as an assistant professor right after that. To a power systems engineering lab. So I hadn't done power systems before. I did electronics at IIT. I did control theory at Stanford. I took one power systems course from a visiting professor, and that was it. But somehow they hired me into this lab, thinking that someone with my background could do something useful. The lab evolved to become the lab for electromagnetic and electronic systems, and then was later absorbed into a bigger lab. And it's nice that that was the lab in which Thomas Kailath did his PhD and was actually the first Indian to earn a doctorate in EE from MIT. That was 1961. And just to line up all these timelines, that was the year that VVS completed his bachelor's degree. Okay, so I got hired to this power systems lab and I had to start learning. And it turned out that there was a doctoral student there already working with a distinguished professor, Professor Schwepping, who was looking at particular small signal stability problems for power systems. So you may or may not know that power systems now, especially, are large interconnected systems, and they can be interconnected on continental scales. So essentially all of North America is one big power system. The US all the way into Canada and some parts of Mexico. I'm showing you here a picture of a small part of the power system in Spain. That's because my first PhD student, Ignacio Perez Arriaga, who's actually a friend of Chandru's as well, was looking at small signal stability in these sorts of systems, not necessarily in Spain, but he's from Spain. So you can see that what this shows is the high voltage transmission lines interconnecting generating stations. All the lower level stuff is suppressed, otherwise it would be even more of a mess. I should kill my phone here, right? So, you know, things that affect the system in one part can propagate to other parts because everything's interconnected. We're used to thinking of the power system perhaps as something that provides a sinusoidal voltage at a fixed frequency from these wall outlets, but things can get more complicated. So let me show you an example of that. So this is the European power system. The frequency is 50 hertz nominally. It's not exactly 50 hertz because you may not know this. The reason, the way the frequency is set in a power system depends on the speed at which the synchronous generators are turning. It's because the synchronous generators are turning at a particular speed that you get that particular frequency. So if the generators are turning a slight bit faster, if they've all settled to turn slightly faster, then you're going to get a slightly different frequency. If there's a disturbance on the system, like for instance in this case a power plant in Spain dropping out of the interconnected European system, suddenly there's less power going into the system, so all the loads are still asking for the same power that they were demanding before. So now what happens is that the generators slow down. What's being fed into the generators as steam is not enough to make up for the loss of this power plant in Spain. So things start to slow down. And indeed you see the frequency dropping from 50 hertz. Okay, so this is a trace of the local frequency measured, over short windows of time, and as you slide along, you see that there's variations in that frequency. So the frequency in some parts of Europe will drop, and other parts it'll drop, and then, well, even here it rises again. So there's clearly dynamics that's occupying a large part of the system. And the question is, how do you understand that? What's down here, this is a frequency scale. On the other side is a power scale, just so that you can track power on a major transmission line interconnecting Germany to France. And what you see is that it was nice and steady before, but now suddenly, because you've lost power in Spain, there's a lot of power that has to come from Germany through France to Spain, and so the power on that line increases. So it's this kind of dynamics that at some stage can start, tripping relays, and you have cascading failures and all of that. But we're looking at just the small signal issues. Now the frequency of this power sloshing around back and forth on continental scale is a much slower frequency than the 50 hertz. So this frequency is something like 0.25 hertz. And these are referred to as the swing modes of the power system, these low frequency modes. And one way to visualize it is by looking at, let's see, I don't think you can see my cursor, but the undriven small signal model for the system at its nominal operating point. So you get a state space model of the type x dot equals ax. If you look at the eigenvectors associated with the various modes of that, you'll find one mode corresponding to this 0.25 hertz. The associated eigenvector will have entries, and they tell you how much these variables are swinging around in that particular mode. All right, so this is how we're used to seeing and thinking about such models. Now you can see the size of this. This particular simulation is for a case of 383 generators, a large number of state variables, and you see that it manages to actually pick up or simulate the mode that was observed in that particular disturbance to a pretty good accuracy. So these arrows are actually plotting the entries of the eigenvector. The eigenvector entries are complex numbers, and so they'll have a magnitude and an orientation. And the picture you should have mentally is that the generators here are slowing down, the ones there are speeding up, and then things reverse, right? So there's a lot of dynamics going on, and this is a snapshot. A simpler picture maybe just think of three masses. Springs and masses is a very good analogy for how you can think about the power system. If you have two big masses like this with a small one in the middle, you can visualize this mode of oscillation where they're going like this, right? And then there's other modes where you can think of the two big masses doing this with the small mass in the middle, kind of stationary. And a third mode where the big masses are more or less stationary and the small one is dancing up and down much faster between them, all right? Now, the question really is which masses are important to represent when you're thinking about a mode in a reduced order way. And you would say that for this particular mode that I'm showing, it's only the two big masses that are important. I can approximate away the small mass. But if I consider the highest frequency mode here with the two masses essentially stationary and the small one moving up and down, I'd want to think of the small one as the important mass for that mode. Now it turns out this right eigenvector way of thinking of it doesn't tell you that. The right eigenvector tells you about the motions, but it doesn't tell you about the importance of the mass for the motion. There's another defect of the right eigenvector, which is if I choose to measure a variable like voltage in millivolts instead of volts, that number jumps by a factor of 1,000, but nothing's changed in the system. So this is not very happy. It's not a good way of setting things up. Now, it turns out that the solution, or one solution, is very simple, which is to bring in what are called the left eigenvectors associated with that mode. And if you take this product of the kth component of the left eigenvector times the kth component of the right eigenvector, you get a scale invariant quantity, which you can think of as as a measure of the importance of that state variable in that particular mode. So we call this the participation factor. It actually fed into some other things we were doing on model reduction for such systems. And it turned out for spring mass systems of the kind I showed you in that example, the participation factor is proportional to the kinetic energy of the mass in that particular mode. So it has the right feel to it. It turned out also that this was very important for model reduction. You could construct a reduced order model that grouped the state variables with high participation and approximated the state variables with lower participation, and you could construct useful reduced order models. So this was how it tied into Ignacio's thesis. Now, actually, I gave a seminar on this. This was, a good 15 years after we started working on this topic, and we'd kind of evolved the topic over that period of time. I gave the seminar in CSA, and I distinctly remember VVS being in the audience in our discussion afterwards. We didn't have many power systems faculty in the audience. I don't remember any discussion with them, partly because this was a systems type thing, and it was the kind of thing that he could relate to. So VVS was there, yeah. Now it turns out, this is a very simple idea. It seems trivial, but it got a lot of traction over the years. We wrote subsequent papers. Our first papers were in 1982, which is about 3 years after I joined MIT. But then it built up over time. Other people picked up on them. It got implemented in software that was routinely used in the power system industry. And so a very simple idea that got a lot of traction. And looking back, it seems unreasonable that something so simple should have done that. The papers are well cited, and Ignacio himself has gone on to a really wonderful career beyond that. He set up a research institute in Madrid, which is a leading institute for power systems research in Europe now, actually, and various other honors. Yeah. I mentioned citations, and I'll mention them again, talking about well-cited work. I have to keep reminding my students and sometimes my colleagues that citation only measures your impact on people who write papers. But there are many other ways to have impact. And so, don't look at Ignacio's citation count, look at all the things he's done in the world. And actually, for a professor, it's not your own citation count that matters. It's all the work your students have gone to do. So, so the many ways to measure impact. But the humble way and the direct way of measuring immediate impact for a professor or an academic is, are you cited? Is anyone paying attention? The other problem with citations is you don't know if the citations are criticizing your paper or have never read your paper but just happen to list it and so on. So be careful of citations. This was another thing that I found interesting in that same article. It echoed for me the time spent in trying to understand power systems, not having had a background in it, and learning, a lot of the learning from the student who was way ahead of me in knowing about power systems. And this idea of an emerging mental picture of the issues at hand when you go to do the modeling and the analysis. So, and this is, by the way, the work of I think his second PhD student. The first was Mansoor Alam, the second was, I think, K. Ramchand, who went on to a very distinguished career. So this is, the first PhD student graduated 3 years after VVS joined the faculty, the second one another 3 years later with publications. Okay, so in parallel a little bit, but more after I started to ease out of the power systems area. I got involved in power electronics, which is related, of course. It's interested in power being delivered in one form when it's supplied in some other form, but the issues are much more extreme than in the general power systems context. In the power systems context, you want the sinusoidal voltage at a fixed frequency. In power electronics, you're asking for more radical things to be done from things like a power supply. So here's, for example, a circuit diagram for a power supply that takes in 220 volts and is asked to produce 13.8 volts. There's a lot of stuff going on here, and you can actually compartmentalize it and tell what each piece is doing. When it comes to the modeling and control part, it turns out that it's just maybe a little resistor and capacitor there that are keeping this thing stable. So you can't be actually designing control with this whole complicated diagram in mind. You've got to distill it down to the essence of the dynamics. And so for the modeling and control type person, that's really the challenge. Now, so I will show you a much simpler circuit which has the essence of one particular type of converter. This is a DC to DC converter. Takes in 12 volts and is asked to put out minus 9 volts. The polarity, you know, is an aspect, the polarity reversal is an aspect of this kind of a circuit. The key thing about a power electronic circuit is you're trying to do this conversion at high efficiency. So the only thing you can afford to have between the source and the load at the other end is something that's lossless, like capacitor, inductor, or transformer, or a switch. So these devices here, the MOSFET and the diode, are not operated in their active region. They're operated as switches. So you'll close this switch, and the voltage will charge up the inductor. The current will ramp up this way. And then you open the switch. That current needs a place to go, so it circulates through the load on this side and charges up the resistor to that negative voltage. Okay, and circulates through the diode. And then when you close the switch again, the diode gets blocked. The inductor current starts up again. So this current is ramping up and down. You can see that here. The variable's ramping up and down. And in steady state, will maintain the minus 9 volts that you want. And this is the steady state that you're seeing here in the initial portion. But what happens if the 12 volts drops to 8 volts at some point? Well, then there's a transient at that stage. So you can see the transient here. This is a simulation. But the switching is, you know, on a very fine scale if you're switching fast enough. So you have to really zoom in to see the switching back and forth. Now for control design, what you want to do is minimize this transient. So it's not useful to have a model that's tracking every bit of the sawtooth. You want some aggregated model that tracks the overall effect. So the question is, how do you do that? The other trace there shows what happens when you have what's called feed-forward control. If you know that the input is dropping from 12 to 8 volts because you're sensing the input, you can actually make a very simple adjustment and make sure that the voltage comes back to minus 9 volts. But feedback control would try and control this transient so that bad things don't happen during that switch. So you need a simple model for designing that. And one way to do that is to think in terms of a local average. Instead of tracking the actual variable, just take its average over a switching period. It's that local average that you're looking to track. In steady state, that will be a constant, because it's the average of a periodically switched thing over the period. But during a transient, this is going to vary, but very slowly. Okay? And this has useful properties. The derivative of the local average is the average of the derivative. Consequence of that is that inductors and capacitors have the same effect on the instantaneous variables that they do on the averaged variables. And an effect of that is you can take the original circuit and construct an average circuit, keeping intact all the linear time invariant components. So the RL and C stay as RL and C. The only thing that's changed is the instantaneous current becomes an average current, and the instantaneous voltage becomes an average voltage. But for the switches, you've got to do something a little more elaborate. So there's a calculation you do that shows that the pair here of MOSFET and diode can be replaced by a transformer whose turns ratio is the duty duty ratio. It's the fraction of time that the switch is on. Okay, so you have to do something a little separate for the switches, but the analysis then becomes very simple. You get a model that will just nicely track the average behavior, and you do your control design with this, and you never bother about the details of the switching. The control design would look at the output voltage and modulate the duty ratio in accordance with the deviation of the output voltage or the average output voltage from its nominal. By the way, each time I walk away from this mic, maybe you're not hearing me anymore, or are you hearing okay? You are, okay, good. All right, now this had all been fairly well established over the years when I was working in power electronics early on. We cleaned up some of the presentation. We factored this into a textbook that I had the privilege of co-authoring, where my part, one of the 4 parts, was on modeling and control. So we had a nice presentation of how to do the averaging, how to exploit the averaging. The lead author here, who's now turning 80 years old, thought it was time we had a new edition because a lot has changed in power electronics. The switches are different, the power levels are different, the switching frequencies are different, the applications are different. So he roped us in, including a former student of his, who's now a very distinguished National Academy member, Perot. And we've just sent off the new edition to Cambridge University Press. It'll appear in May, hopefully. My modeling and control part, it turned out, didn't need all that much revision because the principles of modeling and control didn't change as the devices changed and the frequencies changed. So it sort of felt like it was fundamental. What people were doing over the intervening years was applying those ideas in other settings. There was one new idea, though, that had emerged over those years, and it's an idea that a student of mine and I actually came up with. So what is new here is something that we had done in the intervening years in this new edition. So let me give you an idea of what that's about. There are converters where you switch at a particular frequency, and then when you change the frequency, you get a different response. So if you had a tuned LC circuit, and you drive it with a voltage that's alternating, you'll get a response that's periodic. If you change the frequency, move it closer to the resonance frequency, you'll get a larger amplitude response. But during the transient, you'll get undesired sort of behavior. And what the feedback control has to do is to regulate that. So what you're looking for is a model that describes this envelope, rather than describing the local average. Okay, well, we know how to do that, except nobody seemed to have done it, which was, instead of tracking the local average, define a local fundamental component from a Fourier series. So this is just a Fourier series expression. You take the expression for the fundamental, average it over the switching period, and have it as a running average. That will recreate for you that envelope. You've got to do a little manipulation because this is actually a complex number, but you can construct from the original state space description in a very systematic way a state space description that will track the envelope. Okay, so that idea again got good traction. This, I think, may be my most cited paper. Seth Sanders recently retired as a full professor at UC Berkeley. So when you have the students retiring before the professors, what does that say? But he had a company that does storage on flywheels, and so he wanted to devote more time to that. I wanted to mention that this is also related to the notion of a phasor, which is very familiar in power systems. So if the rate of change of the Fourier component is 0, then the fundamental component of the derivative is just j omega times the fundamental component of the original. We know that from phasor analysis, right? Taking a derivative is like multiplying by j omega for a sinusoid. Okay, so at this point, I was starting to feel that I wasn't very useful in power systems or power electronics. I'd kind of done all I knew how to do with the simple equations. And so I started to leave more and more to the people who were actually building things and the experts in the domain. And I got involved in something quite different through an unexpected route, again dragged there by a student. Thomas Helt is somebody whose thesis committee I served on. He was doing modeling of cardiovascular dynamics. He wanted somebody with a modeling and control background on his committee, so I went there and found that I enjoyed it. And I kind of stuck with that. Thomas became my postdoc after he finished his PhD. And then the next sabbatical I had, I took at a local hospital along with him. And I haven't looked back. So, except for being dragged into writing the second edition of this power electronics book. So then I had to go back to it a bit. Okay, so we set up this group that was aimed at computational approaches to using data to make sense of cardiovascular or cerebrovascular or respiratory or neurological aspects of patient care. Thomas subsequently joined the faculty, and now he's a tenured professor at MIT in our department, and he's set up his own group. And so a lot of the work we started together is now migrated to his group, and he's carrying it forward much more ably than I could. He is actually a graduate of our Health Sciences and Technology program. This might be of interest given the medical school that's coming up here. This is an MD, PhD program normally, but you can also do a program that avoids the MD part, takes a lot of courses with the medical students. And so he's come through that. He's very comfortable in the hospitals and talking to the doctors and so on. So it's a PhD program where you have a home department at MIT and you spend time at Harvard Medical School. And some people then go on to do their MD degrees at Harvard as well. Okay, so what was motivating us is that if you go to an intensive care unit, you see this jumble of instruments. Most of them don't talk to each other. There's no central thing that's making sense of all the data. Each box has its own alarm. The alarms are not necessarily intelligent. You might be given a medication to drop your blood pressure, but you haven't told the limits on the machine that it doesn't have to shoot off an alarm, and so on. So it's a very complicated environment, and you need to be able to give the clinicians some sort of situational awareness, and also to see if you can make use of this data in ways that people are neglecting to use it. You know, you might build an instrument to monitor a particular variable, but if you knew that you would also have another instrument to monitor some other variable, could you combine them to get something better? There's a lot that's measured here, and I won't go through that, but so the basic idea is, can you teach a computer physiology so it can make sense of the data that it's looking at? Now, doing that on a global scale is quite an order. So we're going to do it just subsystem by subsystem. And I know there's at least one physician in the audience. I'll have him keep me straight if I say something that's way off base, but maybe there are others as well. Okay, so we start with the cardiovascular system, and you know how that works roughly, but basically you have the heart pumping blood through through all the organs, and also to the brain, which is very important, and to the heart itself. Okay, so you have a complicated system. This is a cartoon, of course, but it gives you some sense of how things work. This is just the plumbing part of it, but there's also a lot of control, because you need to be able to regulate blood pressure. So it's not enough to just have the heart pumping open loop. The heart needs to adjust how hard it contracts and how frequently it contracts based on what it's sensing. And so, for instance, there's a key sensor here of blood pressure where the carotid artery bifurcates. That gets fed back to the brain, which then decides on some of these variables and feeds things back. There's also a much slower control loop, which involves control of fluid content in the body. And so this is a complicated system. And you can track fluid flow through the system and the blood pressures at various stages. This is a cartoon showing the left side of the heart, the left ventricle pumping fluid through. Here are big arteries, the aorta and other arteries that actually have a lot of elasticity to them. And then you get down to smaller and smaller vessels, all the way down to the capillaries. And actually, some of these vessels at an intermediate stage are very important in controlling resistance to flow. That's an important part of the feedback control loop. And then you get to the venous side, and then things come back to the right heart where they get pumped through the lungs. So that's sort of the path of blood through the system, and these are the associated pressures. And you can see once you get to the venous side and the lungs, you're talking about much lower pressures. In terms of what the heart is seeing, it's really this part that's key. Boy, I'm running slower than I expected to, but can I take a...
We are enjoying it.
Okay. All right. So we're going to model just the left side of the heart. And since we're electrical engineers, we're not going to think in terms of fluid flow. We're going to think in terms of current. We're not going to think in terms of pressure, but rather in terms of voltage. So this is a great thing when you're working in this domain in an electrical engineering department. It's very easy for students to come up to speed because they're very good analogies here. So let me show you what our simple analogy is for that whole cardiovascular system to first order. It's the heart putting in current pulses. There's a capacitor here, which is the compliance of, representing the compliance of the big arteries. And then there's the downstream resistance. And the downstream resistance is called the total peripheral resistance. Physicians actually think in terms of this variable. The medications that you're given to control blood pressure are medications that try to control the amount of blood pumped out each heartbeat or to control the heart rate. Some medications will control resistance to flow by tightening your vessels or expanding them. So this is an RC circuit. This should be taught in every elementary circuits course because it's so motivating. People will present an RC circuit and analyze it endlessly and there's no application given, but this is just a beautiful application. So this circuit will already explain roughly what you're seeing with a blood pressure measurement. The pumping of blood. Every time you deposit blood into the major arteries, blood pressure rises and then it falls, and then comes the next heartbeat. So I'm going to model this as a series of impulses to get the first approximation. Each impulse is going to, in this magenta version, immediately pop things up, and then there'll be an exponential decay because it's an RC circuit, right? So you've already, to first order, explained why you're seeing this, and you can do better than that. It turns out, well, the cardiac output, how much blood is the heart putting out per minute, is an important variable to monitor. Well, we've already seen that the amount of blood that's going in at every heartbeat is proportional to the height of that jump. The proportionality constant is actually the capacitance. So systolic minus diastolic gives you a measure to some proportionality constant of the amount of blood per heartbeat. And then if you multiply by heart rate, you get cardiac output. Okay, well, that's a very simple thing. I don't think there's any hospital bedside monitor that plots that, which is very unfortunate. They'll show you the waveform riding up and down. There's never a plot of heart rate times that difference. This difference is called pulse pressure, by the way. Okay. So this was where we started the learning, or where I started my learning. We had a student actually testing out a wearable device that had an ECG and motion measurements on it. So we took the opportunity to do a little more instrumentation and measure some more variables. Had the student, actually 10 different students, going through various maneuvers. So they would be lying down, and they would sit up, then they would stand, then they would jump in place. They would move their arms, they would walk, run, all of this on the treadmill. The accelerometers would track what the physical activity was. This might have been root sum of squares of the accelerations on the three axes, something like that. But what we expect is that with exercise, your body needs more oxygen. With more oxygen, you need more blood flowing through the muscles. And if you actually do experiments that plot as a function of oxygen intake to support the physical activity, if you plot the cardiac output, you see that it rises very sharply. At rest, there's about a liter per minute circulating out of the heart. But as you get more active and demand more oxygen, the muscles need more blood to carry the oxygen to the muscles. And that rises very sharply so that The overall circulation goes from about 6 liters a minute to something like 22. So one reason to do exertive physical activity as opposed to just slow walking is to get all of this flowing through your body, the juices flowing through your body, you know. In-place activity that doesn't get you asking for more oxygen is not necessarily going to get more blood flowing through everything. Okay, so we were instrumented enough that we could compute this product, pulse pressure times heart rate, and indeed you see that when physical activity goes up, our estimate of cardiac output goes up. And when someone's running, cardiac output again goes up. And the rate at which cardiac output settles after you stop the activity might give you some measures of the general health of the person, right? Because the less healthy you are, perhaps it takes longer for you to recover to a baseline. But this is such an easy thing to capture, and it's not done. This is plotting total peripheral resistance, and again, you can see when there's activity, the resistance drops because your vessels are dilated to allow more blood to flow through, and you can track that very clearly. Okay, I'm eating into question and answer session here. So, by the way, some of you may have heard me give a seminar back in 2019, and I apologize if some of this overlaps. But if you didn't hear me, you may have heard Thomas Held talk about this next piece, and again, there'll be overlaps, yeah. I'm going to race through this, but basically, we went from cardiovascular to thinking about cerebrovascular. We tend to think of the brain as being the computer, so it's all about the nerves and how they compute things, but actually there's a lot of plumbing there. There's flow. There's intracranial fluid, the cerebrospinal fluid that bathes the brain. And knowing the pressure of that fluid can be very important, especially in traumatic brain injury and so on. This point, by the way, that the brain is more than a computer is beautifully made in a book that I hope some of you will look at. It's called The Biological Mind. It's written by a colleague at MIT. And he talks about the cerebral mystique, thinking of the brain as just computer, and he wants to point out that it's actually all of the same messy stuff that makes up your liver and your internal organs is working in the brain too, so you can't neglect the plumbing. I won't go through this, but there's a variety of situations in which you need to know intracranial pressure, but you don't get it because it's very invasive. You have to make a hole in the skull and put a sensor through if you really want to measure intracranial pressure. And so it's only done on the sickest patients, even though it would be of interest to many others, or in many other situations. It's also interesting that if you put two invasive sensors in, they won't necessarily agree on the measurement. So there's quite a spread, even in the measurement of two different sensors in the same brain, invasive sensors. If you could develop a non-invasive method that would have an accuracy comparable to this, then you'd actually be in very good shape. And that's what we worked on. And it turned out to be an RC circuit again. The only difference is, well, here's blood flowing into the brain. Here's the compliance of the cerebral arteries. There's a resistance to flow. But the far end potential is not venous pressure, because intracranial pressure is typically higher than venous pressure. So intracranial pressure closes off the venous end, and the downstream pressure that you sense is actually intracranial pressure. So the flow is determined by the difference between arterial pressure and intracranial pressure, which means if you monitor the flow and the pressure, then you have some information about intracranial pressure. So the way we do it is we monitor arterial pressure in the wrist if it's a patient who has an arterial line, otherwise non-invasively. We take that as a proxy for pressure at the brain. The blood flow into the brain we measure with transcranial Doppler ultrasound. It's a non-invasive measurement. You focus on the middle cerebral artery and you get the flow. And then you back out all of that, and it turns out you can do amazingly well. These are patients who are actually on their way to, in this case, on the way to death. Well, actually in that case too. These are two particular patients, but you can see the non-invasive estimate on top of the invasive estimate, and this is done exceedingly well. This is data collected many years before our work by people who had no idea that we were going to use it this way. Thomas Helt has continued subsequently with many subjects over a large age range, different pathologies, and has shown that this actually works very well. I've been urging him to form a company around this, but he's still deliberating. Okay, so do I have 2 minutes, 3 minutes? Sorry, okay. The thing that we're currently involved in, so I hesitate to leave without saying something about it. There's an instrument that's widely available in clinics and even on ambulances that measures the concentration of exhaled CO2. It's called a capnograph. Exhaled CO2 is a function of time. That's what we call TCAP. Capnography is the name for this modality. And people use it for very limited things right now. For instance, to make sure you're breathing, if they intubate you, they want to be sure that they're in your trachea and not in your esophagus, and so on. You can get a breathing rate out of it. And the reason is you have a very simple waveform. This is for a normal subject. As you exhale, the measured CO2 level goes up because initially the CO2 you're measuring is what's in the atmosphere, which is essentially zero. As you breathe out, all the CO2 that's in your lungs is getting pushed out. That's the CO2 from metabolism. So it rises to a particular peak level, and then you inhale, and then the next breath comes. So this is what capnogram from a normal subject would look like, with a few glitches. It turns out that if someone has COPD, chronic obstructive pulmonary disease, sorry, the shape can change quite radically. And if someone has congestive heart failure, it can be still different. And the question is, can you do this very systematically? I've picked particular cases that show it very well. So this is what we set out to do. If you look at the literature, they compute various slopes, areas. It's a lot of sort of mystical stuff that goes on. And then they try and correlate these landmark features with particular pathologies. We've done our share of that. We had a doctoral student, actually. She did her master's and doctorate on related things. Picking up particular features of this, using machine learning type techniques then to classify the record as having come from one type of patient or another. But it was not really satisfying because we weren't explaining why this waveform has this particular shape. And so we started to look at modeling this. How does the shape relate to the physiology? Because all of these pattern matching things don't really do that. So you look in detail at the structure of the lungs, you realize that the CO2 generation is down here, but there's a whole region, a dead space region, where there's only mixing going on. You construct a model that captures that, and I'm just going to show you the equations. It's very simple, a second order equation for the airflow dynamics, and the first order equation for the mixing. There's a good circuit analogy for that. Again, an RLC circuit to represent the airflow, and the air carries the CO2, so the airflow couples to another RC circuit which represents CO2 concentration. So the combination is a nonlinear circuit, but the pieces are actually quite simple, and the solution is trivial. Okay, so you can go much better than just doing slopes and areas and so on. You can actually closely match the shape of a capnogram, and you can do it for normal subjects, CHF subjects, COPD subjects, and you back out parameters of this low-order model, and those parameters are likely to be representative of these different categories. So you look at the parameters and classify. The parameters are ones that you can communicate to a physician. They have some physical meaning. So this is that's part of it. The other thing is you can actually get the airflow, even though you're not measuring it, you can get the airflow to within a scale factor. So that was our prediction. We weren't able to confirm it till we started to get data from people who are on ventilators. When you're on a ventilator, you have this capnograph, but the capnogram, but you also have airflow measurements. So you're capturing the entire airflow, but you can, on the exhalation branch, you can measure the CO2 concentration. So you can generate the capnogram and you get the airflow. And so we were able to verify, and I'm just going to go quickly to that slide. This was just to show you that this is the state of computation. People don't make any attempt to predict the particular curve. They take the curve as given and then they do all this magic construction, slopes and points of inflection and areas. But you can actually, with this lower order model, fit the entire capnogram to good accuracy. We've also then verified using this ventilator data that the scaled airflow that you predict from temporal capnography with no airflow measurement is indeed a good scaled approximation of the actual airflow. Okay, so we needed to wait for ventilator data to be able to do that. Okay, and then you extract parameters from these models that can then be made the basis of some patient diagnosis. So this is going to be later work. These efforts span many years. So I'm going to kind of wrap up with that. The machine learning story actually is more starting with data and figuring out how to make decisions. So it's going up this way, starting with data. What I've talked about is actually more the other way. We've built on 200 years of people studying physiology, doing stuff with data in different universities and hospitals and so on, coming up with very simple models. And we've been doing sort of the application of the model to the data. I find this diagram to be very helpful in terms of thinking what's going on. If you jump directly from data to decision or action, you miss a lot of the learning that's involved in building these small models. But if you have the small models and the understanding that goes with it, there's a lot more you can do with the data. So that's the general theme. Okay. I've mentioned Thomas Held. We have another key collaborator for the capnography work. But I also wanted to mention two students who started with me at very early stages. One is a junior, just going into her third year, and Karen was starting as a sophomore. She's now a PhD student at Berkeley in a different domain, working on integrated circuits. Karen is doing economics at MIT. But what's been amazing to me is that they've stuck with this through our most recent paper, which is in review, but I'm hopeful. And I just want to say that undergraduates have to get involved in research early, and the inspired undergraduates will really carry you a long way. And in terms of collaborators, my abstract mentioned another book. I have a close collaborator, Al Oppenheim, with whom I wrote another book. But let me finish with this. I've found this to be very true, that teaching or research, it's the professor who learns at least as much as a student, and that's really what keeps us in the business. The reason why people don't want to retire even when they're 80. And I think Professor Sarma had that exactly right. Okay, way over time, but I think I swallowed up all that was I swallowed up all that was planned for the question period, but I'm happy to take some if there. Professor Dikshitulu, if you want to unmute, I can unmute you. Yeah, there you are. Okay.
I'm extremely happy to listen to Dr. Verghese's lecture, and especially the diversity of topics. Sarma also was a person where he was involved in a variety of topics. So that way, his lecture has been eye-opener, especially the last one on the clinical biology. That is very useful. Thank you for exposing us to these new devices. In India, we are just picking up some of these wearables, etc. I have not seen many people, but certainly, we are in the path of growth, and your lecture will be helpful to the audience today. Thank you so much.
Thank you very much. It's a blessing really to have you tune in. Any other questions? I've kept you all very long. Go ahead.
Ask a question because very interesting talk. Particularly the last one, coincidentally, I was asking about it to a doctor. So it so happens that after a long run, for example, when your heart is pumping quite a bit of blood, and you do a squat for about 30 seconds, and then you get up. there is a blackout that happens. And it looks like there is, of course, some amount of relaxation that happens when you squat. And then when you get up, your heart is not pumping enough it's gotten used to the squatting system, but it's not pumping enough. It takes a few seconds to get to the state where things come back to normalcy. Right. I'm just wondering if there is an understanding of perhaps these time scales. Maybe there is an evolutionary basis also for it, but also maybe even
so actually that's quite interesting because, you know, I think I'm not the physician here. I'll defer to the physician, but I think after the exercise, your vessels have dilated. There's probably a pooling of blood that occurs, and I'm trying to find here. So there's a pooling of blood that occurs, so there's probably not enough that's getting pushed up to your brain yet. One of the control loops is one that controls venous tone. Okay, so your veins can shrink to allow less blood to pool there, and so it takes time for that blood to circulate through the heart and get to the head. The body is very interested in maintaining circulation to the head, so but you know, you can't always do that. In fact, Thomas Held's PhD thesis was on orthostatic intolerance in astronauts. It turned out that many astronauts come back to Earth and they can often faint. Their control mechanisms have adjusted during flight to where they're not able to maintain blood pressure to the head without some interventions. So so it's a very real thing. And you're seeing the dynamics of that feedback control in action.
The specific question is about the timelines itself. Do we have some understanding, or the models when you predict it, it looks like you're able to track the shape of the pressure variations and so on.
There is work on modeling the baroreflex, for instance, and the time scales involved. So I haven't looked at it particularly in that context, but people do. There's something else called the Valsalva maneuver, where you clench your insides, sort of tensing your muscles. And then there's a very characteristic transient that blood pressure goes through with very particular time scales. And again, it's these control loops in action. So if you have a continuous monitor for your blood pressure that actually puts out traces, you can try it. You know.
Thank you.
I had a question for you. I think you have seamlessly transitioned from power systems to power electronics to computational physiology to capnography and so on. Is there a running theme in all of these?
The theme is maybe partly that I look for the easy stuff in each of them. So I settle on the problems where I feel that there might be some progress I can make, or the only ones I choose about are the ones where I've made progress, so it's a little hard to say. I think, I'll tell you what, when I was a PhD student, I had an office mate, Sanyan Kung, who would go for a nap and come back with a theorem. And I wouldn't be able to make head or tail of that theorem. It would take me 2 weeks of cleaning up his stuff to get it to a form where I could explain it to myself or anybody else. So I'm just slow, and slow is not a bad thing because it forces you to try and find simple and maybe better explanations for things. So.
What I find is the central theme in all your this one is control and systems.
Yeah.
That is the one
so
central.
My training is to think in terms of dynamics, much more also now and to think in terms of signal processing, because we have data collected in all sorts of settings, and the data needs some processing. That's another thing about the caution about the machine learning. The machine learning will take everything, noise plus signal, without time spent on sort of cleaning up the data to get rid of the noise if you know something about what the noise should be and so on. So the signal processing is a key part of it, but for me the dynamics is a big part of it. On these medical things, we haven't been closing the loop because it takes a lot to be allowed to experiment on a patient. But you can do the open loop stuff, the inference, and then get the inference to the doctors who then do the interventions. So, but yeah, control and dynamics is a big part of it. Without that little resistor and capacitor on that power supply, you wouldn't get it to work.
Yes, that's right.
Can I just, quick question? So on the capnography, again, there's a problem of invasive versus non-invasive ways
Yeah.
of checking. And I think I've asked you this maybe once before, but to check CO2 levels in blood, you really have to puncture an
Yeah.
artery, right?
Yeah.
And that's a challenge.
Yeah.
Just like you've done for the intracranial pressure,
Yeah.
would there be a way?
No, so
right.
actually the CO2 level at the end of the expiration is reflective of the CO2 level in the blood. And so people will use it that way. So they'll look at the what's called end-tidal CO2 level and use it. It's not the perfect measure because it also depends on how good the lungs are at translating. If there's barriers to diffusion in the lungs because of fluid in the lungs, it may not be too good a reflection. But yeah, people use it that way. The temporal capnography is very non-invasive. It's just a little cannula in the nostril and you breathe normally. The volumetric capnogram, which gets the airflow as well, is much more invasive. And that's why you need the ventilator for that, yeah. Sorry, was there another question, Dip, or?
A very general question as ISC enters into its undergrad programs, and you've done all this fantastic work, and you've just come away from a reunion of your undergraduate batchmates. Would you have done your undergrad program differently in relation to what you've done subsequently?
That's a great
How
question.
do you see this?
That's a great
And
question.
I ask this
Yeah.
only because ISC is increasingly entering into undergrad programs.
It's increasingly what?
Entering into undergraduate programs
Yeah.
in engineering.
Yeah, I mean, I regret that IIT was all about courses and periodicals with never, at the time we did it, with never any contact with research. The IIT profiles I see now are those of students who apply to our graduate program, and many of them have done research and of a very good level, and we didn't really have those opportunities or those invitations from faculty to do that. At MIT, we have this thing called the Undergraduate Research Opportunities Program. You have freshmen knocking on your door saying, can I get involved in something? Marty Schlecht, with whom I co-authored this power electronics book, started in his freshman year with John Kasakian, joined our faculty, and then as full professors stepped back to form a company, which is very successful. So yeah, don't count out the undergraduates, and they can do more than apps. So the apps are the easy things, but the things that might have big impact downstream are other things that undergrads can be a big help for.
We have in India what are called internships.
Yeah.
So they're 2-3 months.
Yeah.
Some faculty.
Yeah. But, sort of paying attention to each individual undergraduate student is important. I mean, these two students have been with me on capnography. You can't just say they're two students in a class of 60. I've had them in my classes. But when they come to you for an interaction, those are precious and you have to pick up on them. And not say, see me after the next test or whatever. So, but I don't know if you might have your own answers on that.
No, I was just getting your thoughts on this.
Okay.
Why isn't enough effort being put in to model the different parts of the body, using the mechanical properties or whatever, say like blood vessels, lungs and things like that? What is the current state of knowledge?
I wish I had a slide here. People do very detailed modeling, and their efforts to make it integrative from cellular level to organ level and so on. The mechanical part as well. So for sort of assembling all your understanding of the body, it's a good thing to do. But if you go to a patient and try and, so the more complex a model, the more parameters it has. The more parameters it has, the less uniquely those parameters are going to characterize the patient in a particular situation. What I mean is, if you get, I don't know where I've got my, I don't see, oh, here we go. Okay. So if I have a measurement that looks like this, I don't have a hope of robustly estimating maybe more than 3 or 4 parameters, right? Because I know a low-order polynomial will fit this. If you give me a full patient model that has 20,000 parameters, there's an infinite number of combinations of those parameters that will fit this data. So I don't know which ones apply to the particular patient. So in the patient care setting, you need simple models that are that have few enough parameters that you can uniquely identify them with the patient and that patient's state, the current state. So there is a role for the detailed models because they sort of assemble your understanding of the system. You can try out various things, simulate scenarios that you wouldn't dare to try out on a human subject. And people do that kind of thing. So there are very elaborate models. For instance, on respiration, there is a model called NUMA, which captures all sorts of things, including response to altitude and all of that. It's a huge, detailed model. What they've done is they've taken the learnings from multiple hundreds of studies and assembled them to tweak this piece, and the other. So it's a good representation, but it's not something you would carry to the bedside. There's other detailed models of experiments that have been done in the old days with dogs and with all the numbers put in, but I can't do anything with that for patient care. So there's a big premium on trying to sort of get down to the essence, have reduced models with key parameters that are meaningful to the physician, and estimating them from data available at the bedside. So that's sort of our agenda. Does that address your question?
No, I'm not fully convinced.
Sorry?
I'm not fully convinced.
Okay.
I feel, it's in the long run, the merger of medicine, mechanical engineering, and shall we say, computer science and artificial intelligence is the way to go. Yeah. And I don't think anywhere, students learn, subjects from all the disciplines.
Yeah, they have to become professors and devote 40 years to it, and they learn little bits of this and that.
No, you can. I guess you can try to simplify, yeah, and get some basic, what you call, education or something.
Yeah, well, it's a big agenda.
Is there any place, let's say in US, where let's say one can get a comprehensive education?
Where one can?
Any place in US where one can get a comprehensive education in a short time?
Oh, comprehensive? Yeah. Well.
I mean, that should be the aim of
not MIT.
Education policy makers.
Yeah, maybe in 60 years they'll make fun of how we're doing things, but so I should quit, right? Sorry to have kept you all so long. It's well past what was supposed to be quitting time. Sorry. Thank you.
Thank you very much. Actually, this was a very good opportunity to interact with him, get answers, but we are short of time, and you're all invited for high tea after this function, so you can ask questions actually over high tea, right? So that time we can have. I think the beauty of any theory is the simplicity. So after seeing the title of the talk itself, I was very much looking forward to, right? So using simple RC kind of models, he has explained everything right from heart, even the flow in brain, and multiple other models. So it was really amazing to see how these simple circuits can get that. So thank you very much for introducing us to these models, and especially Verghese also was looking for very simple things and going forward to that. So thank you very much for that thing. My sincere thanks to family of Professor Verghese Sharma. We have Dr. Ramarao, Janaki, her sister, the grandson Kartikeya Sharma, and sister-in-law Janaki. So thank you very much for coming. And you are representing Professor Verghese Sharma, so thank you very much for that. Yeah, thank you. My sincere thanks to all ISC senior professors, Dean Professor Rajesh, and then Professor Chiru, Chairman for CAC, of course Professor Narahari and Professor N. Vishwanathan. I mean, these two are pillars for getting it organized right from scratch. I mean, they motivated us to institutionalize this. And also my sincere thanks to Dr. Kanchana, because she was actually representing the whole CSA students branch actually, although she's sitting there actually, she's the main mover for all the activities right from collecting funds to even organizing this lecture, communicating with all students, etc. So thank you, Dr. Kanchana. And of course, yeah, thank you. And of course, thanks to Dr. Narasimhamurthy, Vayan Shrikant, who are part of VVS Memorial Lecture Committee to organize these things. Thanks to the support staff, Padmavati, and the staff of CBR. So thank you very much for this beautiful lecture and talk. We are really looking forward to multiple lectures in this series, and so thanks to all of you for coming here, and all the audience people here. So with this, we'll come to a closure of this. I request Professor N. Vishwanathan to give a silver plaque to our esteemed speaker.
I'm sorry that your tea's gone cold. We should head out quickly. Thank you. And the flowers.
So thank you very much. Please join us for high tea.